right, following our last discussion, here I just want to play a little more with activity coefficient, introduce the concept of activity and the relationship between the two of them, and then remind you that all of our expressions that we've already worked out can be applied to activity coefficients, or equivalently partial molar excess Gibbs free energy. All right, so the idea was, our definition of fugacity is that for an isothermal process, and so now I'm going to think about mixtures. For an isothermal process, the difference in the partial molar Gibbs free energy of component I at Tp and Xi minus G bar I naught, my standard state or reference state, at the same temperature, but need not be at the same pressure and need not be at the same composition. So for an isothermal process, this difference in partial molar Gibbs free energies is equal to RT log fugacity of component I at Tp and Xi relative to Fi naught at T, P naught, and Xi naught. Okay, cool. So where activity coefficient comes from is here we're going to take our reference state or standard state to be an ideal solution at the same conditions. So if we do that, I get G bar I at Tp and Xi relative to G bar I ideal at Tp and Xi is equal to RT log Fi at Tp and Xi relative to Fi ideal at Tp and Xi. So we introduce gamma, the activity coefficient, as being equal to Fi over Fi ideal. So we introduce gamma, so we define gamma, my activity coefficient, as being the fugacity of my state of interest relative to that of my reference state or idealized state, which in this case is taken to be an ideal solution at the same conditions. Or put differently, that way Fi is equal to gamma I times Fi ideal. So we don't have the log here, so it's reference state value times my correctional factor. G bar I minus G bar ideal, that's equal to partial molar excess. I'm going to bring the RT over, so we get that 1 over RT, G bar IE is just equal to log gamma I. So my activity coefficient is by definition equal to my partial molar excess Gibbs free energy at the same temperature, pressure, and composition. You can think about gamma again as being a correctional term, because log gamma I, again is log Fi over log Fi ideal. So therefore log Fi could be written as log gamma I plus log F ideal. So I can write my fugacity as being equal to my reference state or standard state value plus correctional term. Cool. That's gamma. And so how we get to gamma is we take our idealized state or reference state to be an ideal solution at the same conditions. Before we look at activity, the last thing I want to mention is, if I look at this expression where we take our reference state or standard state to be an ideal solution at the same conditions. So an ideal solution is a system in which all interactions, how do I put this? An ideal solution is a solution in which all of our interactions are exactly the same. So we know that in the pure component limit, all solutions approach ideal solution behavior. When I have a pure component system, all of my interactions are exactly the same. So a pure component system is an ideal solution. So in the pure component limit, all solutions approach ideal solution behavior. So therefore, all of our excess properties go to 0 in the pure component limit. My partial molar excess Gibbs free energy is one and the same. So I know that in the limit, that Xi goes to 1, in my pure component limit, that 1 over RT G bar IE is going to be equal to 0. So therefore, it must be in the pure component limit the log gamma I also goes to 0. Or, more typically, the way it's written is in the limit that xi goes to 1, gamma I is equal to 1. Okay, because if gamma I is equal to 1, then log gamma I is equal to 0. Okay, and this makes sense because, gamma I is just fi over f ideal, or in the pure component limit, fi is just equal to f ideal, right? So gamma I should go to 1 in the pure component limit. Okay, so pure component limit, gamma is equal to 1. All right, so the next concept I want to introduce before we play with gamma a little bit is this idea of activity. Okay, so where activity comes from is, again, I'm going to start by writing down my definition of fugacity. So for an isothermal process, my difference in molar Gibbs free energy is equal to log ratio of fugacity. Okay, so the idea behind activity is I'm going to take my reference state or standard state to be pure I. Okay, so I'm going to look at the pure component limit. So I'm going to rewrite this as g bar I at Tp and Xi minus, now I could just write this as Gi at T and P. Okay, let me put a pure on there just to clarify that it's pure. So I'm taking my reference state or standard state to be pure I, and that then will be equal to RT log Fi at T, P, and Xi relative to Fi pure at T and P. Okay, so when I say pure here, it has to be at the same temperature. It's an isothermal process, but it's going to be at the same temperature and pressure. But now I'm looking at taking my standard state to be pure component I. Remember that reference state needs to be at the same temperature, but need not be at the same pressure or composition. Okay. All right. So in doing so, we're going to introduce a new quantity. We're going to define, we're going to take Fi over Fi pure. Okay, so now the idea is we know that all solutions approach ideal behavior in the pure component limit. Okay, so all solutions approach ideal solution behavior or are ideal solutions in the pure component limit. So rather than just taking my reference state to be an ideal solution, we're going to take it to be a pure component system because I know that pure component limit is an ideal solution, right? It's a real ideal solution, a system that I can actually achieve in the real world. It's not some hypothetical state, right? Because when I take something to be an ideal solution, right, we can think of it as a hypothetical state. So I'm calculating the fugacity of a mixture of acetone and chloroform relative to if that same mixture had behaved ideally, right? That's a hypothetical state. It's a made-up state, not one we would see in physical reality. Well, in the pure component limit, everything is an ideal solution. And so there is an ideal solution we can define things relative to that we can achieve in the real world. Okay. All right, it seems crazy, but, that's the idea. And so this was introduced by Gilbert Newton Lewis, and he called it the activity of component I. Okay, so if I write out the functional dependencies just for clarity, Fi would be at Tp and Xi, and Fi pure would be Tp, would be at T and P. So he defines the fugacity of component I in my mixture relative to that in its pure component state as being equal to activity. So how active a substance is relative to its idealized state. Okay, so he introduces activity. Activity is equal to Fi over Fi pure. Okay, cool. Okay, got the idea. Now we have activity and we have activity coefficient, right? So you think they should be related. Well, they are, right? And so if you think back to chapter 11, when we talked about ideal solutions, where the connection is, remember that the fugacity of an ideal solution, okay, say Tp and Xi, okay, is just equal to Xi times Fi pure at T and P. Okay, so I won't go back and derive this from chapter 11, although it's straightforward, but you go back and look at that. But I know that the fugacity of an ideal solution and that of a pure component system are related. Okay, and so if I were to go up here, okay, and plug that in, okay, so I know Fi at Tp and Xi relative to Fi pure, okay, at T and P, that's equal to AI. Okay. All right. Well, from activity coefficient, we know that Fi at Tp and Xi relative to Fi ideal at Tp and Xi, well, that's equal to gamma I. Okay, and so you can relate them any way you want. But let's see, if I were to divide, say, this by that, so that would give me Fi over Fi ideal divided by Fi over Fi pure would be equal to gamma I over AI. Okay, so Fi terms would cancel, and I get the Fi pure over Fi ideal is equal to gamma I over AI. Okay, great. Well, I know that, again, F ideal, okay, we showed in chapter 11, is just equal to Xi times Fi pure. So if I plug that in, then I have Fi pure divided by Xi times Fi pure is equal to gamma I over AI. Fi pures cancel. So I'm left with AI is equal to Xi times gamma I. Okay. Now again, you could show this equivalence in a number of ways. This is just one that's pretty straightforward and simple. But the activity and activity coefficient are related, right? AI is just equal to Xi times gamma I, just as Fi ideal is equal to Xi times Fi pure. Okay, so activity coefficient and activity are related just via a proportionality constant, which is the mole fraction. Okay, so that's the idea of where activity comes from. But if I go back to gamma, okay, so think about gamma. So we said that 1 over RT G bar IE is equal to log gamma I. Okay, so the last thing to kind of bring things full circle is, log gamma I is just related to partial molar Gibbs free energy. Okay, and remember, it's always a log or exponential relationship, right? Because it's the log of my fugacity, which is related to my molar Gibbs free energy. So just a couple things to point out is, so GE, the excess Gibbs free energy of my mixture, right? We've shown I could write equivalently as sum over I, Xi, G bar I, E. Okay, or if I want to write this in dimensionless form, okay, 1 over RT GE would be equal to sum over I, Xi, G bar I, E over RT. Okay, so it follows that 1 over RT GE could equivalently be written as sum over I, Xi log gamma I. Okay, so I made the comment in our last video, if when we want to calculate fugacity coefficients, we typically do that via cubic equation of state. When we want to calculate gammas, we typically compute those from an excess Gibbs free energy model. And so the idea is we're going to look, not in the next screencast, we'll look at VLE, then we'll look at excess Gibbs free energy models after that. But we're going to develop models, analytic expressions for the excess Gibbs free energy of a mixture, right? And then I get my gammas from that model for GE. I develop models for GE and not gammas, because if I develop models for GE and then get the gammas from it, I can make sure they're consistent and obey the Gibbs-Duhem equation. Okay, but log gamma I is related to GE in this way. Okay. Cool. A couple other expressions to point out that are going to be useful is, so seen as log gamma I is just related to my partial molar excess Gibbs free energy. When I think about partial molar properties, you might think about the Gibbs-Duhem equation. So the Gibbs-Duhem equation would be applicable here. Okay, so remember that's going to be my zero sum requirement. So it'd be sum over I, xi, dg bar I, e. Okay, and we can, bring the RT in here if we want. Differential, just need to write it right. G bar I e over RT. Okay, so I know that this has to be equal to 0. Well, I could equivalently substitute my partial molar excess Gibbs free energy with log activity coefficients. Okay, so the Gibbs-Duhem equation is just as applicable to activity coefficients. Key though to remember is here we're talking about log gammas. Okay, yeah, and if I needed to calculate log gamma I via GE, right? Well, it's just equal to my partial molar excess Gibbs free energy, right? So remember, in general, if I need to calculate partial molar excess Gibbs free energy, that'd be the differential of n times, in this case, it'd be GE over RT with respect to Ni, a constant TP, and then J, right? So I could calculate it, and this would be equal to log gamma I. So I could calculate it as a differential of an expression for dimensionless excess Gibbs free energy. And if we had a binary system, we had worked out some simplified expressions for that. Okay, cool. So Gibbs-Duhem equation is applicable. Log gamma I is related to excess Gibbs free energy. And then the very last thing that I'll point out just to mention, okay, is now I'm going to have to jog my memory, but I believe it was, let's see, our expression for the differential of dimensionless G was negative h over rt squared dt plus v over rt dp, I believe. Okay, so equivalently then I could write this for the equivalent expression for excess properties, for partial molar properties, for partial molar excess. So I would have that dg bar IE over RT is equal to negative h bar IE over RT squared dt plus v over RT dp. That'd be v bar IE. And so equivalently, I could write this then as the differential of log gamma I. Okay, so the differential of log gamma I, the differential of the log of my activity coefficient of component I, is negative h bar IE over RT squared dt plus v bar IE over RT dp. So if I was interested in, say, temperature dependence of my activity coefficient, here you got it, right? So this would tell me that partial log gamma I partial t constant p would be equal to negative h bar I e over RT squared d, negative h bar I e over RT squared. So the temperature dependence of log gamma I is related to my partial molar excess enthalpy. And then if I wanted pressure dependence, d log gamma I dp, a constant t, would be v bar IE over RT. Okay, and then just one last point, because we're going to talk about GE models later, is I could write this expression up here for G. So I know that I could have d GE over RT then is equal to negative HE over RT squared dt plus VE over RT dp. Okay, cool. And just as a note, remember HE is equal to delta H of mixing. VE is equal to delta V of mixing. Okay. So a common assumption that's made is we said we're going to calculate gammas from these excess Gibbs free energy models. And so a common assumption is that the excess Gibbs free energy of a liquid phase is independent of pressure. And so just to give you an idea of what that means is I know the differential of GE over RT. So with respect to P, okay, so what is the pressure dependence of GE? Well, it's going to be equal to VE over RT. And so when the GE models make this assumption that GE is independent of P when modeling liquid phases, what they're really assuming then is that the differential of GE over RT with respect to P is approximately equal to 0. That would only be true if my excess volume is approximately equal to 0. And it's not so much that VE, delta V of mixing is always equal to 0, but typically it's numerically, the contribution of delta D of mixing is going to be much smaller than the effect of delta H of mixing due to intermolecular interactions. So it's not so much that it's always 0, but it can typically be neglected with respect to, or as compared to delta H of mixing. Okay, so I just want to mention that because this is an assumption that comes up, just so you can see what it looks like. And then, just for completeness, so if I wanted the pressure dependence, or temperature dependence, so a constant P, that'd be negative HE over R T squared. Okay, cool. Okay, and so hopefully that's enough on activities. Next, we'll talk about how to use them to calculate vapor-liquid coexistence. We'll look at some excess Gibbs free energy models, and then we'll be ready to tackle the problems.